So what does the air standard Brayton cycle really look like? Well, the air standard Brayton cycle essentially breaks down the gas turbine engine and its operation into four processes that are repeated on the cycle. So first of all, the air enters the compressor. So between 1 and 2 here on the PV diagram, this represents the compressor. So the air is compressed in the compressor, and we assume that it's compressed adiabatically and reversibly. So there's no heat transfer and it's reversible. You should remember that that is isentropically. So we've got an isentropic compressor. Then after it comes out of the isentropic compressor, it's got a much higher pressure, slightly smaller volume, specific volume, and it's then passed into, well, in reality it would be the combustion chamber, but we model that as just as a heat exchanger. That is essentially the combustion chamber there, where we add heat into the working fluid. The thing about the Brayton cycle is that happens at approximately constant pressure, so the combustion chamber remains at approximately constant pressure. We then have, once we have this high temperature air leaving the combustion chamber, it then passes through the turbine. So processes, process 3 to 4 here, it's when it's passing through the turbine and it's expanding. So the air expands as it passes through the turbine, and that turns the turbine essentially. And that's done again, we assume, adiabatically and reversibly. So again, isentropic. So it's an isentropic expansion to the turbine. We then assume that once it leaves the turbine, well, in reality, we know that it would be just exhausted back into the atmosphere. But what we assume is that same fluid is actually going to be passed back to the compressor, but it's just going to be cooled first. So we basically pass it through a heat exchanger and let some heat out of it, which we know that we have to do to complete the cycle. Air is cooled again at constant pressure. We assume it's cooled in sort of atmospheric pressure, so it's pretty constant pressure conditions. So that's essentially the key point for the air standard Brayton cycle. We see that same cycle on a TS diagram here. So again, we have air entering the compressor from 1 to 2. So we've got a slight increase in temperature as it goes through the compressor. You'll notice the entropy stays constant because that is an isentropic process. So the entropy S is constant. We then have the heat exchanger process, the addition of heat through the combustion chamber, which is at constant pressure, but it is bringing in a lot of heat and increasing the temperature substantially. We then have the highest temperature. So that is the highest temperature in the cycle. High temperature fluid is then passed through the turbine and allowed to expand through the turbine. And as it expands through that turbine, that is what's creating our network output. Some of that work is actually used to drive the compressor. You see, it's dictated by this little shaft here. And that's really what happens. The turbine drives the compressor. So you have a network output of the turbine, and then we have the fluid being passed back to the compressor. And before it's passed back, we have to dump that heat through into the atmosphere, again at constant pressure. So that is a heat exchange process again, but we now have a loss in temperature from 4 to 1. The temperature decreases and we've got heat coming out.